If we combine linear independence and spanning, this forms a basis. The formal definition is if we have v1 to vn is a basis. This is true if and only if every vector in our vector space V can be uniquely written as a linear combination of these basis vectors. So we have v equals a1 v1 plus an vn, where the a's are the coordinates of our vector v. Let's take a look at some standard bases, which are just the bases we normally use in certain spaces. For instance, if we have Rn, it's just coordinates with n components. The standard basis for this would be 1, 0, 0, so we represent that as E1, and then E2 would be 0, 1, a 1 in the second component, and zeros everywhere else. E3 would have a 1 in the third component, zeros everywhere else, and En has a 1 in the last component. Another space we have is Pn. So this is all polynomials of degree at most n. Well, first of all, let's look at what a polynomial looks like. A0 plus A1x plus A2x squared plus all the way up till AnXn. The standard basis would be 1 and zeros everywhere else, x squared, and then xn. So again, it's sort of similar. We have 1 in the first component plus 0x plus 0xn, and we have 0 plus 1x plus zeros everywhere else, and the last one would be zeros everywhere, except for in the last component we'll have 1xn. The standard bases can be thought of as the simplest way to generate every single element. For example, we need to be able to generate a constant, an x term, an x squared term, all the way till an xn term. Next, if we look at mn, all m by n matrices, we need to be able to generate every single element. It's going to be big, so we have 1 and zeros everywhere else. To generate the second one, we have 0, then 1, and zeros everywhere else. And we'd go through generating every single element in our matrix, all the way till the last one. Let's introduce one last term, which is dimension. Dimension is the unique number of elements in any basis of a vector space V. So for instance, in Rn, the dimension would be n, because we have n vectors in our basis. If we had less than n vectors, we wouldn't span the whole space. And if we had more than n, it would be linearly dependent, and we would have a redundant vector. So it would not be a basis. What's the dimension of Pn? Well, how many vectors do we have? We have 1, and then x to the 1, and then all the way till x to the n plus 1. The dimension of m by n, all m by n matrices, would be m times n. Lastly, it's important to note that bases only exist in finite dimensional space. If we're talking about an infinite space, there's no such set of vectors that will span the entire space, so you can't generate a basis. One example of an infinite space would be all functions. If you put in the basis, say, 1, then x squared, then what about sine? Okay, if we add in sine, what about cos? Then you add in cos. Then there's always going to be another element you have to add. So it's impossible to form a basis. Let's try an example. Let's find two bases of U, where U is the set that contains all 2 by 2 matrices that have the property A times that matrix is itself. So let's see what this means. If we have X is a general matrix, A, B, C, D, where these are just real numbers, then in order to be included in U, we have the property 1, 1, 0, 0 times this matrix is itself. This means that 1 times A is A, plus 1 times C is our first element, and our second element will be 1 times B plus 1 times D. On the bottom we get 0A plus 0C, and then 0b plus 0d. We can then equate a plus c equals a, and b plus d equals b. If we isolate c, move the a to the opposite side, we get c equals 0, and likewise, we'll get d equals 0. So this means that all matrices in U have to have the form a, b, 0, 0, where a and b are just real numbers. In order to find the span of U, let's separate a and b, because they're completely separate variables. So we can write this as a, 0, 0, 0 plus 0, b, 0, 0. Now we can factor out the a and the b, and a linear combination is just the definition of a span. Since U is spanned by two matrices, let's check if we need both of these matrices. If these two matrices are independent, we'll need two matrices in order to form a basis of U. Independence is pretty obvious here. If we say S times the first matrix plus T times the second matrix equals our 0 vector, which would be 0, 0, 0, 0 in this case, we clearly see that S equals 0 and T equals 0 is the only solution. So one possible basis, I'll call this B1, would be these two matrices, because they have two properties. One, they span space, so they span U, and secondly, they are independent. To find a second possible basis, we need two matrices that are in our set U that are independent. So let's try 1, 1, 0, 0 and 0, 1, 0, 0. These matrices both are in our set U, and they're not the same matrix, and they're not multiples of one another, so we can conclude that they're independent. To show this explicitly, we can write it as S times the first matrix plus T times the second matrix equals the 0 vector. Now, what two equations do we get? If we were to add them together, we get S plus T, 0, 0. S equals 0 and S plus T equals 0. Therefore, T must also equal 0. So these matrices are independent. Since the dimension of U is 2, meaning that there's two vectors required to span the space, so every basis of U will have two vectors. And we've found two vectors in U that are independent. They have to span the space. If you didn't see this, you could write it out explicitly. Write the vectors in the span of U is a linear combination of the vectors in the span of B2 and vice versa. This would show that the two spans are equal. In either case, we arrive at the conclusion that B2 is another possible basis of U.